Thank you, Piszek, for inviting me here for this conference and give me the opportunity to present our recent results on the hybrid photoelectrical systems on titanium nanostructures. Usually we'll use titanium nanotubes. And so here's the outline. And in principle, the presentation line is, the main line is just how to improve the photocurrent generation in titanium nanotubes, and also how to extend the light absorption of the tubes to the visible light. Okay, for solar cells. Well, as Bishek said, we have one of the oldest spectrophotometer here. And we operate connected with a PG stat from Metron, operated with a software Nova 1.0. It still works. Thank you for that. And all experiments were done in the free electrode cell, which is here, and the sample was always mounted from outside to the cell, and was the working electrode. As an electrolyte, we always use natrium sulfide. So this I can skip because we had a very nice presentation in the morning, I think. So I will start with the preparation of the tubes. This is very simple. You can prepare it by anodic oxidation of titanium foil in the presence of fluoride anions, either suitable electrochemical conditions. And it depends the conditions on the length of the tubes we will require, or the diameters of the tubes. That's the case. So on the picture on the left, you can see a top view of the tubes. You can see that they are well organized, mostly as a hexagonal state. And here you can see the cross-section of the tubes. And they have typical rings here around. And sometimes the rings connect the tubes between. Okay? And well, the tubes are originally, when you grow, amorphous. I have to convert it to the crystalline phase. And here we have two types of crystalline phases: anatas, which is indirect band gap structure, having the band gap energy about 3.2 electron volts, and rutile, which is a direct band gap semiconductor with the energy of the band gap around 3 electron volts. And as was said yesterday, indirect band gap semiconductors have a longer charge carry lifetimes compared to the direct band gap structure. So that's the reason why anatas is better to use for photoactive applications. And here are plenty of applications, for example, photocatalysis, hydrogen evolution, gas sensors, fuel cells, dye-sensitized solar cells, energy storage, medicine, but also food industry for the nanoparticles, or pharmacy, and so on. Well, there was always debate if we apply the same growth conditions on the titanium foils, which were purchased from different producers, because there are always a little bit different composition, purity, also the surface roughness is different, and so on. And we wanted to know if the properties and morphology is the same or not. So we always converted them to we bought it from Sigma Aldrich, Advanced Materials, and Goodfellow. Here you can see that from Goodfellow we used 2 different purities, and this was specifically also polished. We converted them to the anatas, and then here we did the analysis of the diameters and the length. Here you can see that all of them were approximately 1 micron thick, and the diameter was about 80 nanometers. And this is the result from the photocurrent measurement. What we found that one of them was extremely efficient. And we did it maybe 3 times, and this picture is always the same, actually. We didn't know what has happened, but here you can see that even if we expose it to maybe 1,000 seconds, there's a limit of the shutter, of the spectrophotometer, there is no fading. So that means it's real and stable. And what is the origin of that? We wanted to know. And then we did an experiment using electron energy spectroscopy where you can see the local structure defects, especially we did it for titanium L2 free edges. So here, this is an inspected window. Oh, come on, sorry. So that we can measure both titanium nanotubes and also titanium foil. So in the figure B here, this is a titanium L2 free edge of the foil only, and there's practically no difference between them. But if you look at the figure C, there are tubes only. You can see a big difference. For example, from a sigma Aldrich, there is a typical splitting here, which is for Anatas, while for the GOFF, which has a very nice photocurrent, here is a feature from titanium 3+. So it's doped structure. This also from the oxygen K edge, and this is the same story. This is a typical for Anatas splitting on the K edge, oxygen K edge, and this is with the doped structure, so there is oxygen vacancies. So we can conclude that the excellent photocurrent for the GOFF is the titanium 3+ embedded in the structure. And this is not surprising. There are plenty of literature. You can see that titanium 3+ extremely support the photocurrent density. And this is one of them. You can see that the black curves here on the states is a white titanium. The red is, they call it brown. There are some titanium 3+, and the blue is a black titanium. There are plenty of titanium 3+ structure. Also, the ground tube are usually double wall system. So that means that it has two shells, inner and outer shell. The inner shell is a porous material somehow. The outer shell is a compact titanium oxide. Okay, and then you can see it here on the SCM figure. We use usually two type of nanotubes, 5 micron and 15 micron length. Yes, this is a top view of the top of the tubes, and this is a top view of the bottom of the part. And here, I'm not sure if you can see it. For example, here, this is the outer shell, and this is the inner shell. Yes? And we can remove the inner shell very easily. This is a procedure how to do that. If you have an amorphous material, you can preheat it to 150 degrees. Then to etch it in the piranha solution, which is peroxide sulfuric acid, for a few minutes, and then clean it in water with ethanol. And then you have to get this nanotubes, which is the bottom part of that, and you can see just only single wall structure. And here is the photo response of that. So the black curves are always single wall structure. The dashed red structure line is a double wall structure. And if you can see in all cases, both cases, the IPCI value is higher for single wall structure rather than double wall structure. And here also, if you look at the transient, you can see that a single wall structure has higher photocurrent density, and also it's faster. So yes. So that means that there is delay in response, and probably due to some defects on the surfaces of the tubes, usually they call it, there is some oxygen vacancies and so on. Okay. We can also modify the titanium nanotubes in a different way. We can completely reconstruct the wall of the tube. We can use it ALD. We use a Banach, and just you can use a titanium tetrachloride as a precursor for titanium, and water as a precursor for oxygen. And you can do several cycles, and then here you can see the top view of the tubes. Come on. As blank tubes, and this which are coated by titanium oxide. And this is our bottom part. Okay. And this is the photo response of them. So here you can see the black line here is a blank structure. But when you increase the number of cycles, On titanium, this is 50 cycles. This is 200 cycles, which corresponds to 11 nanometers of the titanium, but from one side, so 11 plus 11 on the other side. But when we increase even more the cycles, the IPCI value decreases again. So we found the optimum conditions, optimal thickness of the titanium layer for exactly for IPCI value. Here is also the transient. We can see that the blank structures also, there's a very delayed time for the response. And when we increase the number of cycles, or let's say the thickness of the titanium on the top of the tubes, we annihilate these defects in structure, and then the photoresponse is very fast. So any application of these tubes, we usually do as a case study photocatalytic degradation of methylene blue. Okay? So here, the black line corresponds to the blank structure. When we increase the number of titanium on the structure, the kinetics increases. So it's faster, but after 200 cycles, it's again slower. We believe that is due to the fact that when you increase the thickness too much, then the active area is smaller for the catalytic. I'm not sure if it's true, but we believe that it's like that. Okay. So far I showed you that we can somehow modify and support or to increase the photocurrent density by modification of tubes. But our goal is to extend the absorption of these tubes to the visible light, because the plan of the ERC project, which was granted to Jan Macák, and we did it through this whole experiments, was to do some hybrid solar cells based on titanium nanotubes and secondary material. Okay, so and as you know, the titanium doesn't have any response in the visible light. So, and it's possible somehow. There are some papers that they say that if you combine with organic dyes or perovskites or other materials, you can sensing these tubes to the visible light somehow. But the question is if you can do that with the chalcogenides, which are also one of the best inorganic material for solar cells. And you can say, yes, we can actually, and there are many possibilities how to do that. For example, you can do it using a spin coating. That's a solvent solution. You can dissolve the material, just drop it on the top and dissolve. Or you can do electrodeposition, chemical bath deposition, solvent deposition, salt thermal deposition. You use atomic layer deposition, and also you can treat it as a reaction of vapor phase. That means, for example, sulfurization. Okay? There is another assumption, and it means that there are some technique, for example, ALD, that it's difficult to deposit 1 micron thick film. You need lots of material, and it's impossible. But for example, if you have nanostructured material, you need only a few nanometers, and you can get the same effect mass. If it's vertical, yeah, that's true. So that's another assumption we would wanted to verify if it's true or not, actually. So we started with spin coating because at the time we didn't have ALD. And this is the just pioneering work that Jan Macák did. Okay. And they dissolved arsenic sulfide. This is amorphous material actually, and it's perfectly dissolved in the propylamine very easily. They did modify the concentration of the arsenic sulfur in the propylamine, and then they deposited it on the titanium nanotubes. They're about 15 microns long and about 130 nanometers in diameter. And they found that when they increased the number of, when they combined this chalcogenide with the tube, they increased the response in the UV light. So that means that they somehow annihilated the surface states of the tubes, and also they have some absorption in the visible light. Unfortunately, this absorption is not as big as we wanted. wanted something like here. Okay, so it needs some improvement. So in that case, we try to do two things. One is to make tubes with a large diameter. So these tubes have 250 nanometers in diameter, and also we used crystalline material instead of amorphous. And as a case study, we used tin sulfur cyanide, which is also possible to dissolve in propylamine, but you need a single droplet of hydrazine just to initiate the dissolution. Because this material was reported in 2004 by MITSI, they dissolved only in the hydrazine, and this is extremely toxic and nobody wants to work with it. Okay? So, and here is a picture of the blank tube, and they are coated. So you can see that there is a massive difference. And here you can see IPCI value and those wavelengths. The blue is the blank structure, and the red curve is the modified titanium nanotubes. Well, this is the same story practically, that we improved the response in the UV light. In the visible light, it's a little bit better than before, of course, but still, we're not satisfied. And also here you can see that even if the structure is black, quite dark, we don't see any material on the top. So that means that the material was penetrated inside the tubes. I mean, not inside it, but on the walls. We don't see them on the SEM, any material on the top, because when we did it on the short tubes, with small diameter, they're only compact layer. Okay. So since we weren't satisfied with the spin coating, we tried to do the electrodeposition of copper indium cyanide, which is a chalcopyrite semiconductor, which is also very promising in the field of photovoltaics. And it's easy to make a solution which contains copper sulfate, cyanic acid, and indium sulfate in the ice water. The deposition was done in the range of 0.8 volts versus reference electrode, and takes about half an hour. And what is interesting here we have blank tubes. When we did the electrodeposition, we had this nice granulated structure on the top. It's also inside, of course. I don't have this cross-section, but it's inside. But this material doesn't have any photoresponse. We had to cyanize it. I will show on the next slide why. And the cyanization is done in the quartz sample. Just place the sample selenium, seal it here, then evacuate it to 10 to minus 3 Pascal, seal it completely here at the end, and then you can put it in the furnace and expose it to temperature. We reactively used 450 degrees for 10 minutes, and it's now perfectly cyanized structure here. And the reason why I have to cyanize it here, before the cyanization, come on, that's a black structure. We don't have any crystal peak from the copper indium cyanide. After crystallization, we have quite strong signal. So that's the reason before we don't have copper indium cyanide structure. And here's the photoresponse. So here's the IPC of the blank tubes. And here we have the heterostructures, IPCI. And here you can see that we almost get what we wanted, actually. Almost 60% across the visible light spectrum. So in this case, we found the pathway that for the inorganic sources can be done by heterostructure material using titanium nanotubes and chalcogen material. Of course, electrodeposition and sulfurization, cyanization is not really very nice, so try to do it in a different way. So here we found that it's, I don't say found, but in principle, the interface between the absorber and the tube plays a role, okay? So if we extend, if you make the interface larger, then you can get more material on the tubes. And you can do that in two different ways. Either to reduce the diameter of the tubes, or just to grow longer tubes. And we wanted to verify this assumption, and we used shorter tubes with the same length, but different diameters, 35, 56, and 90 nanometers, and the long tubes, which were almost the same, the diameter, but the length was from 1 to 130 micrometers. So, and for this reason, we used ALD deposition. As a precursor, we used dimethyl cadmium, and for the sulfur source, we used sulfane. And here you can see, if you do several cycles, we did actually repeat 40 cycles. We had about 6 nanometers of the cadmium sulfide on the top. And the cadmium sulfide is one of the best material for solar cells in the visible light as well. Well, we used, again, Banach ALD machine. And now, and for short tubes, we use a normal flow. The normal flow means that you put the pulse of the precursor to the chamber, you will leave it through the chamber and it goes through the chamber to the outlet and leave it away, throw it away. If you use a stop flow, you pass the chamber, precursor to the chamber, then system is closed for a certain time so that you get the time to material or the precursor to go up to the bottom of the tubes. So diffusion is important in this case. So, and what's the results? We started with the short tubes. So we deposit cadmium sulfide on the top. Here you can see SEM pictures of the blank and deposited structures. Here you can see that the thickness of the balls is different. So you can see definitely that there is a cadmium sulfide. Okay, can you see here? Also here. Also, it's not really clear seen, but here also you can see in the cross section that the material is inside everywhere the tubes. So, and this is a photochemical response of pure titanium as a support. And you can see that there is no difference if you use a titanium tube with having a 35, 56, or 90 meter in diameter. Okay? But if you have with cadmium sulfide, the story is different. So this is the reference blank tube, and this is with a 90 tubes with a diameter of 90, 56, and 35. And this is in line of our assumption, actually, because if you have small diameter, you have higher surface area, actually, per area. So that means that we have more cadmium sulfide in the material, the structure. Also, you can see that transients are very fast. So this is quite nice material. Also, for the deposition of ALD, the incubation time for nucleation and also for the growth, it's important. It depends what substrates you have and also crystallinity of the material. So for this experiment, we crystallized or preheated the titanium tubes to different temperatures, to 300, 400, 500, 600. And you can see here that when you preheat to 600, there is already a rutile structure. Yes, so as I mentioned at the beginning, anatase is better for photoactive structure, but here we have rutile structure. And the question is, can we use rutile structure as a support for heterostructured material? And here is the result. So when we preheat it to 300, This is the IPC value, 405, and for 600, we have one of the best signal ever. So we believe that also rutile can be good support for that. And the reason is why here, if you look at it. So this is a SCM samples decorated by cadmium sulfide on preheated sample to 300, 4, 5, 6. And here you can see that there are particles on the top. So that's the reason why we have lower IPC value. If you have 400, if you deposit cadmium on the preheated sample of 4, 5, and 6, you can see some, say, compact block of crystalline structure. And the detail analysis shows that also the opening of the diameters became small here, closer. So that means that on the rutile you can get more cadmium sulfide than the another structure. And here you can see why. So if you look at the XRD, you can see here that you have some amorphous background still. So that means that samples preheated 300 degrees, there is an anatas, but also still some amorphous phase. On the preheated sample on the 400 degrees, there is a little bit as well, but after that it's completely crystalline. And we found also that the cadmium sulfide here is a hexagonal phase. It can be. And TM shows something interesting here. So this is an interface between the titanium oxide and cadmium sulfide. These lines are atoms from the titanium oxide and this from cadmium sulfide. And exactly on the interface you can see that these lines touches. So that means that it's something like templated crystallization or templated growth. That means that why we have some nice crystals on the top. And so what's happening if we have long tubes? Here's the photoresponse of the long tubes. And you can see that the longer tubes, the worse signal we have. That's because there are lots of defects on the surfaces. Also, you can see here that the transients became worse, delayed. But when we coded it, you can see this is for 1 micron and 115. They said that it should be 130. You can see as well that here and here, that there are material already. It's closer. It's at the top, outside and also inside. This is from the top, this is from the bottom part. You can see in the bottom that there is cadmium sulfide, perfectly done. Here, you can see from STM and EDX as well that we have cadmium sulfide. Yes, this is a signal. Cadmium is black and sulfur is red. So it's perfectly coated on the both edges and also in the interior of the tubes. And here are the results. So this is a reference sample, and then all of them had around 70% of IPC value. And what was interesting here, that when we increased the length of the tube, we also moved the absorption to the visible light, almost to the infrared spectrum. If you look at the energy band gap of the cadmium sulfide, you can see it's 2.4 electron volts, which is about 500 nanometers, which is here. But we can absorb the light somewhere about 750 nanometers, which is about 1.6 electron volts, which is something interesting. And this is the reason why. There is an extension coefficient of the cadmium sulfide. Here should be a band gap, but here we have absorption tails. And if you deposit material with absorption tails on the nanostructured material, which has a significant length, then you can promote the absorption of those absorption tails. So that's the reason why we have very nice absorption until 750 nanometers.
Are you shining light from the?
Yes.
You try to go along the tube. With
Yes,
light.
exactly.
But still, the wavelength of the light is of order of, 400 nanometers of visible, right? 500 nanometers, and you have tubes that are like smaller in diameter. So this light, if you look at it as a wave, it should not enter those.
No, they don't as well. This is a simplified picture. Usually you have to take a complex of tubes. Yes, there is lots of multiple scattering and absorption. That's the reason why we promote the absorption tails. Okay. And here is a little bit different topic, but basically this is the same story. This is chalcogenide materials, maybe transition metal. The chalcogenide and the disulfide is a typical representative for that. So it crystallizes in a hexagonal van der Waals structure. So this is a covalently bonded triplet layer, which is then bonded with a weak interaction of van der Waals structures. What we can see is N-type semiconductor, and the bulk has indirect band gap about 1.1 electron volt, but the one layer structure is a direct band gap structure, which has a band gap about 1.8 electron volts. And this material has many applications, and as a bulk, you can see that solid-state lubricant, for example. And then photocatalysis, if it's a layer, one single layer or more, you can have it. Photocatalytic, electrocatalytic evolution of hydrogen. It's important for optoelectronics, actually, and sensors, energy storage, and if you know, also for data storage applications. Here we prefer tellurides rather than sulfides, but you can use it as well.
And what type of sensors are those?
Well, that's many sensors. Biology sensors, whatever.
Oh yeah, this is okay.
You can also for radiotherapy, for example, that you can increase the temperature. If you put it to the body, for example, disulfide, you can shine on it with the light about 808 nanometers. I think it's a typical wavelength for medicine, whatever. And then, since usually the cancer cell likes lots of energy from the body, the molybdenum disulfide accumulated in the body, in the cancer cells. And if you enlighten this part, then you will increase the temperature significantly for about 15-20 degrees, and the cancer cells will die. Okay. So, and since our goal was making heterostructures from titanium tubes and molybdenum disulfide here, here we use also ALD. This is a precursor for molybdenum, actually, but you can use also molybdenum pentachloride. This is no problem. And we use sulfane as a sulfur precursor. So here is a STM picture with EDX, how the molybdenum and sulfur is on the top of the tubes. You can see how it's distributed, and you can see that it's homogeneously distributed. Well, this is only for 2 cycles, and I'll explain you why. Here, after that, we did many cycles, different cycles. But only if you have 1 or 2 cycles, you can see nice photoresponse. After that, you don't measure. If you have maybe 10 or 20 cycles, you don't see any photoresponse. We don't know why. Possibly this is due to the fact that there are van der Waals gaps which can block the electron passing through to the tube. That might be the origin. We don't know, but possibly.
How about reflection of light? If you had
but it's completely dark, actually. I don't know.
Black.
It's black.
Yes, it is black. But this is why. So it absorbs everything.
Yeah, of course. It absorbs.
Okay, good.
Yes, and this material, as a case study, we use also photocatalytic degradation methane blue. Here you can see also that this is for the blank structure with 1 cycle, 2 cycles, and then again decrease the rate. Also, this structure can be used in lithium batteries, for example. is also case study. And so here you can see areal capacity versus number of cycles. This is the pristine nanotubes. And this is decorated with a molybdenum disulfide. You can see that it's quite stable and also improved a little bit. And another way how to prepare transition metal chalcogenide is just sulfurization of titanium nanotubes itself. And then we do it in a port samples, then place a sample, sulfur, see it again, and now we have to find the optimum conditions, of course. So we expose it at different temperatures, 250, 300, 350, 400, and 450, and also different times, 7:30 and 3 hours. Okay? And here is a top and cross-section. We use SCM pictures. Here we can see that until 350, we don't see anything on the top and on the cross-section on the walls. But from 350, you can see here, maybe you don't see a little bit small crystal, a rather large crystal, but there are some. And with increasing temperature, the crystals become smaller. But on the other hand, you can see these crystals are bigger. Smaller in the size, but you can see them. Here you can see that very nice crystalline structure here already. And here probably these are very fragile. Actually, after 3 hours, are extremely fragile. And here is the photoresponse of the tubes, and you'll sulfurize at 250, 300, and 350. See, here you can see that photoresponse increases. But after that, if we sulfurize it at 400, 450, and a different time, again it decreases. Okay. And here's, I wanted to know why, what's the origin of what is the best structure on the tubes from the crystalline point of view. So in this range of 2 theta, titanium doesn't have any crystalline feature, any reflection. If you anneal it, if you sulfurize at 250 degrees for 7 minutes, here's one feature. We believe that is titanium sulfide pure with oxygen, so titanium sulfur oxygen structure. After that, if you sulfurize at 350 or 450 C for 7 minutes, here's titanium disulfide. It's a typical feature of titanium disulfide. And after that, if you sulfurize it to 450 C for 3 hours, there is a typical titanium trisulfide structure. Okay, so the best photoresponse have only titanium disulfide structure. Also, here's some applications as well. So this is a decomposition of the methylene blue. And here you can see that the best conditions are if you sulfurize at 450 C and for 30 minutes. That's probably because for the catalytic applications, you need edges rather than basal planes. Yeah. And also here was a lithium battery test. You can see that is a pristine titanium tubes. It is sulfurized. We use it for titanium. This was titanium sulfur-free structure only. And you can see that's quite improved and stable. Well, so I will conclude my presentation here. So I show you that modification titanium tubes can be improved, can improve the photokinetics and also IPCI. Also, a combination of chalcogenides and titanium is a promising way for realization of new sources devices, which was the goal of the ERC project, and also some formation of heter structures of titanium transition metallic chalcogenides and titanium nanotubes, which are good for photocatalysis and energy storages. Also, I should present a team which participated on the presentation. So this was a group leader, the owner of the ERC project, Hanna Sofa, Martin Motoa, and Silvan did the nanotubes and kinetics. I mean, decomposition, photocatalytic decomposition, some stuff. Rauzape and Jan Prickel They did the ALD coatings, for example. Louis Gramatko did SCM pictures and X-ray diffractions. And also Philip Dvořák and Jonathan Rodriguez-Pereira, they are specialists in XPS. Okay, so it's an acknowledgement of the funding, and thank you for your attention.
Great talk. You show on 34 or 35 slide IPCE with photocurrents. Maybe
This one?
earlier.
Yes.
No, earlier, 33.
Yes.
Earlier. Okay, yes. So there is IPCE for 600 nanometers, about 60%. And could you explain why you have so low photocurrents for this IPCE?
You mean here?
On the pink one, curve red one.
60 is...
You have IPCE almost 60%. There's 60%, yes? IPCE.
Well, this I don't know actually.
Okay, this is not yours?
No, I did it, but honestly, I don't know why it's here drop actually.
No. My question is, you have 60% of IPCE.
Yes.
So you should have much more higher photocurrents.
On the right.
I see here. Well, that's a good question actually. I think this is the way also how you treat the data actually. Because sometimes, especially in chalcogenides, you could see that you don't have a background flat. You have a little bit curved, and you have to substrate the background. And that might be the reason why you have a little bit different photocurrent.
Yeah. Okay, thank
But
you.
those two photocurrents, I mean, in your system and here, they do not need to agree because it depends on the slits, for example. So there are a couple of...
But on the other hand, if you calculate the photocurrents from the transients, it should be IPC the same, right?
Yeah, you can do this.
Yeah. So maybe this is the data treatment. Yeah.
Maybe this slide also. When you write here that the band gap is 162, so
No,
but it is not the fact the band gap.
This is not the band gap.
Yeah, because it seems that it is changing, but really it is because this Orbach.
Exactly,
level,
exactly.
So it is not this reason. Yeah.
Yeah.
Okay. But when you use these systems with nanotubes for photocatalysis or so on, when you have tubes and the tubes are attached to the substrate, the
Yes.
solution is not penetrated well, the tubes inside. Usually it is just on the top because you do not have the exchange of the solution inside the tubes. Why it is better to have the tubes in such the case? Because in my, I think that it does not help in photocatalysis because mainly your surface is working, not the length of the tubes.
But I would say that the length plays the role because, well, you have the inner and outer, interior and exterior. The exterior, definitely, the tubes from the outside will work because you can get a solution there. This is definitely. I mean, if you have tube, you have the inner part and outer part.
Yeah.
And you said that you cannot get the solution to inner part.
No, not inner part because it is chopped. It is impossible to go because you have chopped tubes. So as you have a very thin capillary but closed, you do not put the solution inside.
To the tube, but the outer of the tube you can. Because there is a gap, there are gaps, definitely.
Yeah, but porous material may have also...
Okay, yeah, this is true. So that's the reason why I try to do some, just remove the bottom part. Yeah, that might be the reason why we cannot do a spin coating, for example.
Yeah.
This is the same story actually. We can do outer part, but not the interior. You can see that into interior, if you have maybe 1 micron thick film, then you have just only 200 nanometers inside.
Yeah.
You are right actually. But the exterior works perfectly.
Okay.
Because it's the same as porous material.
Yeah. And you also talked about evolution of hydrogen with the use of molybdenum sulfide.
Yeah,
Have you done any measurements with this? Because it is really active when it is single layers, not thick one, because of
you're right. And actually, we haven't done it for molybdenum disulfide, but we did molybdenum diselenide, and there is a very strong signal. And also only if you have only a few cycles, because it's very tiny crystals on the top, almost invisible. But you can see just something like lines on the SCM. So it works nicely actually. And we have a paper on that. And also molybdenum ditelluride as well, it works nicely. Yeah. Well, please ask.
At the beginning, you have shown that when you have substrate and you can produce titanium 3+.
Yes.
And have you used it for photocatalysis?
No.
Because when you use many times, probably this 3+ is again reduced, oxidized to 4+.
The reason is why we didn't do that was that this type of titanium foil is pretty expensive. So we wanted to know only what's the origin of that, and if we can the same. That's because reproducibility is one of the key how to do whatever. And if the tubes are not reproducible, then
they are much better than others. So
of course. But we did at least the growth of these tubes and measure it for photocurrents. It was always the same picture. Okay. But we don't know if it's due to the purity or that the surface was polished. Also, crystallographic of the titanium could play the role, because you know how the titanium is made by rolling. So it might be the case.
Okay, thank you very much for the talk.